All right, Calculus 30, section 1.1 lesson here. We're going to talk about linear functions, okay? I know we've talked about linear functions before, a little bit of a review here. But we're also going to talk about something called the tangent problem. And the tangent, for those of you that don't know, a tangent is a line that touches a curve, a circle or a curve, at one point only. And I'm going to talk a little bit more about that as the lesson goes on. But linear functions and tangents, okay, we have to talk about both of those for this section. So let's review quickly what a linear function is, what it looks like, what are the aspects of a linear function, and how do we generate a linear function given 2 points. That's the first bit of this video, okay, of this lesson. So a linear function is often in this format. Y, or f of x, that's function notation, equals mx plus b. You should know that m is the slope of the line, and b is the y-intercept of the line. And they are just regular number constants, okay? So the slope of the line is given by the rise, that is the change in y value, divided by, that's the change in y value between any 2 points, so this point and this point, let's say. So the difference between the y values, change in y, divided by the difference in the x values of the point. X there, x there. So here's y, there's y. So here's delta, delta y, and here's delta x down here. Now, in order to find the slope, we need 2 points here because we've got to find the rise over the run. 2 points. Very important that we need to use 2 points to calculate the slope this way. Okay, it's super important to realize. You may think that's pretty obvious. We need 2 points, a point here and a point there, let's say. But notice a couple things, that the slope of the line is constant because it's a straight line. Another way that we can represent this change, this slope, okay, the rise over the run, is the rate of change of y with respect to x. So a slope can be understood as how is y changing as x changes, okay? Difference in y, difference in x, all right? Now, we've done this before, but I'm going to go over just really briefly here the method by which you can generate an equation, a linear equation, given 2 points. So this example 1 says find a linear function whose graph passes through the points -1, -1, and 2, 5. So if we were to graph that really quickly, right, -1, -1 might be about there, and 2, 5 might be about here. So we're looking for the equation of this line. Well, how do we do that? Well, we need a couple things. The first thing I think that we would need here is the slope. Because remember, the format of a line is y equals mx plus b. That's one form of a line. So it would be really helpful to have m. And we can find m by finding the slope, or the change in y divided by the change in x. And that is y2 minus y1 divided by x2 minus x1. And that's going to help us find the slope. So y2, if this is the second point, because it's listed second, this is going to be y2. So 5 minus, here's y1, minus a -1, divided by 2 minus a -1. That's 5 plus 1 is 6, really. And that's 2 plus 1 is 3. So the slope appears to be 2. When you simplify that, it appears to be 2. Okay? Now I could check that. If I drew a real careful graph, you could count that. If you went 1, 2, 3, 4, 5, 6 spaces between -1 and 5, and if you went from -1 over to 2, that's 3. So 6 divided by 3 is 2. You see that? So we've got our slope. Now I don't have a y-intercept. I don't have a y-intercept. A y-intercept would be in the form of, like, it would be 0 and then some number y, right? That's a y-intercept. But I don't have that. I'm not given that. Could I figure it out? Maybe. There's a better way to do this, though. I don't know how many of you remember the point slope form. The point slope form of a line looks like this. And you might notice that it's simply a variation of this slope formula. See that? It's simply a rearrangement of the slope formula. But this can give us the actual equation of a line if we're given the slope and a point. I'm going to take one of the points. It doesn't matter which point. All you need is one. I'm going to take this one right here, and I'm going to plug the x and y values into this format for a line, and I'm going to get an equation for this line. So this is really important, this point slope form. And this y stays as y because you need an x and a y in there to have your equation for the line. So y1 is 5. Now it doesn't matter what's y1 and y2. We're just taking this as y. So y minus positive 5 equals the m, the slope that we found is 2, times x minus the x1 is simply the x value of the point you're taking. Okay? We know that point is on the line, so I'm going to create an equation for the line given the slope and one of the points on the line. Now you could leave it like this. That's okay. I would probably prefer you to expand and get it into y equals mx plus b, okay? So that won't take us too long. So y minus 5, let's do this 2x minus 4. Let's add 5 to both sides, and we get y equals 2x plus 1. Okay? Y equals 2x plus 1 should be the equation of our line. Okay? Now, why do we need to know how to do that? Well, because as I mentioned, we're studying tangents here, and tangents are straight lines, and we are going to be asked to find the equation of the tangent line. Okay? So we're going to need to find the slope and use one of the points on the line, and we're going to get an equation. So this is going to come in handy a little bit later. Okay. Yeah, if you have any questions, just go ahead and let me know. Chat in or raise your hand or whatever if you have any questions at this point, but I'm going to be moving on here after this example. So, any questions? All right, should be pretty basic review stuff for this stuff. Now, let's take a look at what happens if we don't have a straight line, okay? Don't have a straight line. If the function is not linear, like this function right here, this blue graph right here is curved, right? It's kind of just a little snaky. We can find the slope of a secant line. Now, a secant line is a line that connects any 2 points on the graph, okay? So, for example, this point, a random point, and this point would have a secant line connecting them, okay? So this is a secant line connecting, let's say this is x1 and this is x2. So this would be f of x1, this value right here, and this would be f of x2. That would be sort of this value up here, right? So any 2 points on a graph you can draw a secant line connecting those two. And that secant line actually can tell us a lot of information. So depending on what the graph represents, so for example, if this graph represents, let's say the meters that you have traveled from a starting point here, meters, and this is seconds, okay? So this could be a map of, someone walking away from a certain point. You're going a certain number of meters in a certain number of seconds. And then over here, looks like you're coming back a little bit, right? The meters is now going down over here, and you're coming back as time passes, okay? So you're changing position over time. Now, the slope of this line right here would be rise, or meters, divided by run, or seconds. So again, change in y would be in meters. Change in x would be in seconds. So the slope of this line would be meters per second, or this could be your average velocity between this time and this time. Okay? Now, I've got a little more detailed graph up here, so hopefully you can see this here now. This is on Desmos, and this is a secant line connecting 2 points, and this graph is pretty similar to the one I drew. Now, if I change one of the points, like this point right here, this red line, still a secant line, but it represents the average sort of velocity, okay, between this time right here and this time over here, okay? And there would be a point here where it looks like the average velocity might be 0. And why is that? It's tough for me to actually pinpoint there. Let's see if I could grab it here and move it. Oh, I can. So this is a flat line, the slope is 0 because the position was positive here, and then it becomes negative, and it kind of balances off, positive, negative. So the average velocity is the average, the change in distance divided by the change in time. So the change in distance here between these 2 points is 0. So the average velocity is 0. So let's just move this back around. Okay, so there's a secant line like this, and I can find, now watch this, I can find the average velocity between any 2 points here, you see? Any 2 points. And I can calculate the slope of that line, which in this case might be average velocity. Okay, so let's talk now about tangents. Okay, so a tangent line is a line that intersects a curve at only one point. Okay, only one point. So it's as opposed to a secant line, a tangent line has only one point on the curve. So here's a secant line. Ready? Watch this. Down here, here's a secant line connecting this point and this point. And let's see, whoops, this might be a tangent line. Oops, I missed that a little bit. This might be a tangent line right here, touching the graph at just one point. Okay, that's a tangent line. So tangent lines are very, very important in calculus. And if we go back to this little intro page here, let me see, introduction, look at this. So notice this red line, okay? That's a tangent line, isn't it? And differential calculus is, we use tangent lines all the time. It's very, very important. So when we explore tangent lines, we are doing something that's really, really important for calculus. The slope of the tangent line, okay, represents, now let's go back to this graph before I answer that, okay? Watch what happens if I bring, let's say, these 2 points closer and closer together, okay? That line is looking almost like a tangent line, isn't it? So watch this. If I bring that point close together, that is getting close to a tangent line, and that's going to be very important here very soon. But this is still the difference between 2 points in time. If we take a look at a tangent line, so here's a graph, okay, this is a tangent line right here. See that? And if I move that along a little bit, a tangent line only touches the curve at one point. So if this was a distance versus time graph, just like the first one I showed you, okay, just like this one, then the secant line represents the average velocity between time A and time B. What does the tangent line represent? What does the tangent line represent? Well, the tangent line for the same exact situation would still represent a velocity, but it's not a velocity between 2 points. It would be a velocity at exactly 1 point. See that? And a velocity at exactly one instant in time is called an instantaneous velocity. Okay? So the slope of a tangent line, in some cases, is an instantaneous velocity or an instantaneous rate of change. And I think we need to write that down. I think it's going to come a little bit later, but the slope of a tangent line is the instantaneous, whoa, how do I spell instantaneous? Instantaneous rate of change in whatever the situation is, okay? So if it's speed, it's the instantaneous velocity, let's say, in a question, okay? But the tangent line is the instantaneous, so in one instant of time, what is the rate of change? So think about this. In a situation where a person is walking down the street, okay, if you took the average velocity and you said, okay, so this person covered 100 meters in 10 seconds. Well, the average velocity would be 100 divided by 10, or 10 meters per second, right? But this type of question, you could ask this. You could say, what was this person's exact speed at 2 seconds after he started? Well, you think, well, would you say it's 10? Well, it might not be 10. What if he started running and then got tired and started to walk, then his rate of change is changing over the interval. And so that's what's happening here. That's why a tangent line is so important. In calculus, we can find instantaneous rates of change. But the problem, now here's the problem. The problem is calculating this slope. Because we only have one point, we cannot calculate the slope in the same way as we could a secant line. Because a secant line, we have this point, and we can find out what the average is. For a tangent, we only have one point. So what's the change in y? For 1 point? 0. What's the change in x? 0. That's a problem. 0 divided by 0 is not a slope, right? It's not a number that's useful. So the slope of the tangent line can't be calculated the same as 2 points can. I think that's supposed to be way. Could not be calculated the same way. Okay. All right. So let's think about this then. Let's think about this. First of all, the point of tangency is something that's very important for us to understand. The point of tangency would be the point at which the tangent line, let's try this again. The point at which the tangent line touches the curve. Wow, I just cannot draw freehand today. We're going to do it this way. Okay, technology wins. Come on, technology, help me out here. Okay, come on. There we go. Okay, that's a tangent line. And guess what? P here is the point of tangency. There it is, the point of tangency. You see that? Okay, so when I talk about the point of tangency, we're talking about the moment or the point at which the tangent line touches the curve, okay? Now, how are we going to find the slope of a tangent line? And this is the first major concept in calculus that you need to understand. Okay, it's really this concept of a limit. Okay, a concept of a limit. So here's my tangent line, and I can find a tangent line looks like anywhere on this curve. Okay, but I don't know what the slope is because I'm only given 1 point. So let's say that this point right here that I'm circling, that's the point of tangency, and I want to find out what the slope of the tangent is. Well, check this out. I'm going to say this. If I take the slope of this red line, is that close to a tangent line? No, it's not. What happens if I move this point a little bit closer? Is that close to a tangent line? Well, let's see, that's the tangent line there. So you can kind of see what that looks like. As I move these 2 points together, do you guys see that this secant line is starting to get pretty close to what the tangent line is? And this is the most important thing of this whole lesson is this. Okay? If we consider secant lines where the points are closer and closer and closer and closer and closer together, then what's going to happen is we are eventually going to run into a point where the 2 points are infinitely close to one another. And that means that they're going to behave almost like those 2 points were 1 point. Okay? And notice that I'm going to try and put this on 1/2 and let's see. I'm going to pull this one out, put it on the other half. Oh, there we go. Beautiful, beautiful. So notice, look at this. Oh, this is great. Those 2 points are extremely close together, and this is the point of tangency. That slope of this red line looks to be virtually the same, doesn't it? Okay, my scale's a bit off. My scale's a bit different, but you can kind of see that these are pretty close, eh? So they're pretty close. So the point is, as we bring the points closer and closer together, the secant line starts to approximate the tangent line. So I'm going to draw another. Oops, that's not what I want. Watch this. Okay, so I'm going to move this like that. Okay, so this secant line that connects PQ is not at all like the tangent line. But what happens if I move to P and a different Q, one that are a little closer together? Well, then that line starts to look a little bit more like the tangent line. And you see that? And if I move this, so that's this point right here. If I move this point closer and closer, hopefully you can kind of see what's happening here. I'm going to change this so that the points are really close to one another. And there they go. They start to be almost the same. Okay? And so as the 2 points come together, the secant line approaches the tangent line, which I have here in these 2 paragraph statements. Okay? So let's read these together. Considering this situation that we just talked about, with 2 points getting closer and closer together, all right? If Q was to be brought closer and closer together to P, and the slopes were calculated at each step, then the slopes calculated would begin to approximate the slope of the tangent line at P. I'll read that one more time. If the point Q was brought closer and closer together to P, so here's Q, it's coming closer to P. Well, let's do P up here. Okay, then the secant line connecting the 2 starts to approximate or look very much like the tangent line. The slopes of the lines, as 2 points get closer together, will reach or approach a limit. This limit is the slope of the tangent line. So I will kind of conclude this idea by going back to my graphs here. Okay. So again, if I'm over here like this, okay, so as this second point gets closer and closer to the first point, all right, then this secant line, now there's going to be a limit here. So let me zoom in. Look at how close we are. It's pretty close. Can I get closer? Yeah, I can. Look at how close that is. Oh my. So there's a limit here. Like the concept is pretty soon these points are going to like be exactly the same point, right? So as we approach that limit, and now check this out. It's amazing. It's super, super close. Like I am like thousands and thousands, millionths of a difference there. Like just tiny. So if I zoom back out, look what happens. See? Look at that. Look at that. Beauty. That's pretty much the tangent line, you see? Huh? Isn't that great? There we go, and make these the same. You see that? They're pretty much the exact same. But I've actually used 2 points that are super close together. See? 2 points. So as those points get closer together, they start to look exactly like the tangent. But there's still 2 points. Even though it's very close to being just 1 point, there's still 2, and that's what's important. There is a limit. As we get closer and closer together, the end of this approaching each other, as close as one can possibly get, that end of that limit would equal the slope of the tangent line. The very end of that process, okay? As these points got closer and closer together. Okay, do you have any questions for me at this point? Those of you that are in my class here right now, do you have any questions that you'd like to speak out here? Okay, so let's talk about the notation then, all right? So we write this, we would express this as a limit, okay? Now here's the expression, and I want you to write this down. You're going to write this L-I-M. You're going to write this thousands of times, okay? Almost. And it's going to be the limit, okay, as Q approaches P. So remember in our little diagram, right, we had something like this. Here's P, here's Q, right there. So as Q approaches P, and when we talk about the slope of PQ, so the limit of the slope of PQ as Q approaches P, that's how we would say it. The limit of the slope of PQ as Q approaches P equals the slope of the tangent line at P. And this limit notation is new. It's very new. and it's going to be very important. So the limit of what? Well, the limit of the slope of the secant line as Q approaches P, as they become very much the same point, right? That limit is going to equal the slope of the tangent. Let me put it in, let me just do one more example in different terms, okay? In different terms. So think about this. Okay, so let's say that I want to know where you and I will meet on the street if you walk from your home and I walk from my home. Okay? So let's just say I'm walking towards you and you're going to walk towards me. All right? Now at the beginning of that situation, we might have an idea based on how fast I walk and how fast you walk and the routes that we're going to take. We might have an idea about where we're going to meet. But we won't really know for sure unless we actually start walking, okay? So here's me over here, and here's you, and we are walking towards each other, okay? And as we get closer to each other on the street, we have a really good idea of where we're going to meet, okay? Now think about this. You and I are walking towards each other on the street, and just before we get to each other, just before we bump noses, okay, we look down at the street. And right in between the two of us is the exact point that we're going to meet, right? But yet, we're not at that point. We are not standing on that point because you and I cannot occupy the exact same space, right? So we're nose to nose, and we look down, and right in between our toes on the ground, that's the exact spot where we meet. That's our limit, okay? That's the limit. Just like this, the 2 points are getting closer together, and at the point where they would become 1 point, that's the tangent. That's the point of tangency. And the slope at that point would be the slope of the tangent line, okay? So we still have 2 points, but you know where that limit is taking you to, okay? And I will want to show you just one thing here, and I do not have it up here for, just give me 1 second. Okay, so this is in your textbook. This is in your textbook now. Now look at this curve. See the parabola there? Okay. We have P and we have a point Q. Okay. So if P and Q are separated this much, that secant line does not look like the tangent line. But as Q gets closer and closer to P, that means as the X values of these points gets closer and closer together, and they've put this in a chart, okay, as the difference in the X values becomes smaller and smaller and smaller and smaller right here, look what happens to the slope between those two. It starts at 3. If the X values were 2 units apart, the slope is 3. If the X values were 1.5 units apart, the slope between the 2 points is now 2.5. And look what happens. Do you see these numbers? They start to approach a certain limit. And so if you take a difference between the X values here and the slopes, it looks like it's approaching 2, exactly 2. Well, if you take a look at points on the other side of P and bring those Q points up to P and closer, look what happens to the slope. The slope starts at 1 when the 2 points are far apart, and then as they get closer, look what it's approaching. And this part right here, this line right here, you see how they're both approaching 2? Like they're almost exactly 2, both of them, but they're approaching 2 from a different side, from the top, one from the bottom, whatever. So this is what it looks like mathematically in a chart, okay? And yeah, so that's the concept that we are taking a look at here today. Okay, so that's 1.1. That's the tangent problem. You cannot find the slope of a tangent line by taking just 1 point. You need the slope of, you need to find slope with 2 points, and we let the 2 points become closer and closer together. If we calculate the slope between 2 points that are really close together, we can guess what the slope of the tangent point would be. Okay? And just a note, this is a tangent line to the curve. This is not a tangent line to the curve. Okay? This is a tangent line to the curve here. Okay? All right, so you might want to read this section in your textbook. Go over this a little bit here if you want. But anyways, that's the lesson for today, unless you have any other questions. Here's your assignment, and I will be going over some of these homework questions in a different video section. All right, there you go.